Have you ever been standing in the chemistry lab holding a little strip of red litmus paper
Mm-hmm.
and you're staring at a beaker of, some clear liquid, maybe it's ammonia or maybe something organic like aniline, and you dip that paper in,
And instantly,
instantly snap, it turns blue.
it feels like magic every single time.
It is. Or maybe you've just walked past the open chemical cabinet at the back of the lab,
Oh, I know this one.
and that sharp, fishy, sort of pungent smell just hits you. You know the one I'm talking
I
about.
definitely know the one. That smell is unforgettable. That is the smell of amines.
Exactly.
And that color change on the litmus paper.
Yeah.
That is chemistry happening right in front of your eyes.
But here's the thing. We see the color change, and we definitely smell the fumes. But have you ever stopped to wonder why? What's actually going on at that tiny microscopic level that makes that paper turn blue?
That is exactly what we need to unpack today. We're going beyond just the smell and the color.
Welcome to another deep dive. Today, we are tackling a super important topic for your Class 12 board exams. We're looking at Unit 9, Amines. But we aren't trying to memorize the whole textbook in one go. We're focusing on one thing, the structure of amines.
And honestly, this is the perfect place to start. A lot of students think organic chemistry is just a list of reactions to memorize.
It certainly feels like that sometimes, especially the night before an exam.
It does. But it feels that way only if you don't understand the architecture of the molecule itself. We aren't just looking at shapes for the sake of drawing pictures.
Right.
We were looking at why these chemicals behave the way they do.
So structure dictates function.
Precisely. If you truly understand the structure we discussed today, the shape, the electrons, you will automatically understand why amines act as bases. You get why they act as nucleophiles. You won't have to memorize it. You'll be able to predict it.
That is the goal. Our mission for this deep dive is simple. We want to make the structure of amines so clear that you can actually visualize it with your eyes closed.
A mental picture.
Exactly. A mental picture that will help you secure those marks in your board exams.
Let's get into it.
Okay. I want to start at the absolute bottom. Let's assume I skipped class 11. I know nothing about this family of compounds. Break it down to the 0 level for me. What actually is an amine?
Right. So at the simplest level, an amine is basically a cousin of ammonia. Remember the formula for ammonia, right?
1 nitrogen, 3 hydrogens.
Right. So an amine is essentially that ammonia molecule where you've done a swap. You take it and you replace 1, 2, or even all 3 of those hydrogen atoms
With something else.
with carbon-containing groups.
Okay, what kind of carbon groups are we talking about here?
It could be anything, really.
Yeah.
Alkyl groups like a methyl or ethyl chain. Or it could be aryl groups like a benzene ring attached to it.
So we're just swapping out the parts. The main body, the core, it stays the same.
The core remains the same.
Okay, I want everyone listening to try and picture this. We need a shape. So imagine a pyramid. Not a flat triangle on paper, but a proper 3-dimensional pyramid.
Like the pyramids in Egypt, but, much smaller.
Much, much smaller. At the very top, at the apex, sits a nitrogen atom. And at the base, forming the 3 corners, you have your attachments.
Right. In ammonia, those would be the 3 hydrogens.
And for an amine, we're just popping off those hydrogens and plugging in our carbon groups instead.
That's the perfect way to visualize the skeleton. But
Ah, I knew there's a but.
there is a massive but. And this is the part that students so often miss. We need to look at what the nitrogen is actually doing, the particle behavior.
Okay. What is the nitrogen doing?
In an alley, the nitrogen atom is, it's sput hybridized.
Okay, pause there. Sput hybridized.
That is one of those terms that gets thrown around in coaching classes all the time.
All the time.
Let's decode it for the student who's a bit rusty. What does that actually mean for the shape?
It just means there are 4 zones of electrons surrounding that nitrogen. Now, think about our pyramid. We mentioned 3 connections at the base, correct? Right. The bonds to the carbons or hydrogens, so that's 3 zones.
That accounts for 3 of them. But spine implies 4.
So where's the 4th one?
That is the million-dollar question. The 4th domain, it holds a lone pair of electrons.
A lone pair.
Yes. It's a pair of electrons that isn't bonded to any other atom. It's unshared. It's just sitting there on top of the nitrogen.
So it's basically invisible in the stick diagrams we draw in our notebooks.
Often, yes. And because it's there, taking up space, it actually pushes the other bonds down a little.
Ah, okay.
This is why the geometry is pyramidal and not flat. If that lone pair wasn't there, the molecule might be planar. But the lone pair pushes everything else away.
That is a key distinction. It's not flat. It's a tripod. It is a pyramid.
Correct. And if you want a definition that's safe for your exams, strictly NCERT level, then just remember this. Amines are organic compounds derived from ammonia, in which one or more hydrogen atoms are replaced by alkyl or aryl groups, with the nitrogen atom retaining its lone pair of electrons.
Retaining its lone pair. That really seems to be the headline here.
It absolutely is. In fact, let me point out a huge misunderstanding trigger right now.
Please do. What do students get wrong?
So students look at the diagrams. They see the nitrogen, the 3 lines for the bonds, and maybe 2 little dots for the lone pair. And they treat those dots like they're just decoration.
Just some extra ink on the page.
Exactly. They confuse it with a bonding pair. But you must remember, in Amines, that lone pair is not bonded to anything. It's free. It is available. And that availability, that is what drives everything.
Everything.
Basicity, nucleophilicity, the smell, the reactions, all of it comes from those 2 little dots.
So it's basically open for business.
It is an open parking spot waiting for a visitor. That's a good way to put it.
Okay, let's try to lock this in with an analogy, because Poisson and electron domains can feel a bit abstract. I found a comparison in the notes that I really like. Think of the nitrogen atom as a socket wrench.
A socket wrench. Okay, walk me through that.
So the nitrogen is the head of the wrench itself, and it has, let's say, 3 handles. Those are the hydrogens.
Right.
You can swap those handles out for different attachments, different alkyl or aryl groups.
Okay, I'm with you. You're changing the grip of the tool.
But here's the key part. No matter what attachments you put on it, the mechanism of the wrench, the part that actually grabs the bolt and does the work, that's still there.
And that mechanism is the lone pair.
That mechanism is the lone pair.
That's a very strong analogy because it shows that the lone pair is always present. It's like a magnet built into the tool. It doesn't matter what's attached to the nitrogen. That magnet, the lone pair, is still sitting there, ready to attract things.
Exactly.
Yeah.
It is the functional core. You can dress up the molecule, but the lone pair does the heavy lifting.
There's another way to think about it if you prefer biology to mechanics.
Oh, okay. Let's hear it.
The human hand analogy. Imagine nitrogen is the palm of your hand. Your fingers are the bonds to carbon or hydrogen. They hold everything together. But your thumb.
The thumb is the lone pair.
The thumb is the lone pair. It sticks out, separate from the fingers. And what does the thumb do? It grips things. It pushes. It's the active part of the hand.
That's good. The fingers are structural, but the thumb is functional.
Precisely.
Now, I have to play the skeptic for a second. I know a lot of students are listening and thinking, okay, pyramid, lone pair, socket wrench, but why do we even study this specific shape? Why does it matter?
It's a fair question. Why is this concept in your syllabus? It exists because without understanding this specific shape, and specifically that lone pair, we can't solve the problem of predicting reactivity.
Predicting reactivity. Break that down for us.
Well, think about history. Early chemists, they saw amines accepting protons. They saw them acting like bases. They just didn't know why.
They knew what happened, but not how it happened.
Exactly. This structure, the electron theory, finally explained it. It's that electron-rich lone pair. It's the source of the power. If you don't understand that the lone pair is sticking out, you can't explain why it grabs a proton from somewhere else.
So if you don't get the shape, you can't predict the reaction. You're just guessing.
You're just guessing. And in a board exam, guessing is very dangerous.
Very true. Okay, I want to guide our listeners through a mental movie. So if you are somewhere safe to do so, maybe just close your eyes for a moment.
Let's paint the picture.
Okay. Picture a nitrogen atom. Let's make it a bright blue sphere floating in space. Now, coming out from the bottom of the sphere, pointing downwards, are 3 bonds. These form the base of our pyramid.
Those are your bonds to carbon or hydrogen.
Right. Now, for the important part, look at the top of that blue nitrogen sphere. Pointing straight up, like a little antenna or flag, is a cloud. Let's make it a glowing red or orange cloud.
And that is your lone pair.
That red cloud is the business end of the molecule. It creates a partial negative charge right there.
And that is the crucial detail. That red cloud, that lone pair, is what makes the amine reactive. It is what reaches out and grabs a proton.
Okay, you can open your eyes. Hopefully that image of the blue pyramid with the glowing red antenna sticks with you.
If you can hold on to that image, you basically understand the soul of amine chemistry.
The soul of the chemistry. I like that. Okay, let's connect this back to the real world. We started with the litmus paper. Why does it turn blue?
So think back to your red cloud antenna. When you put the amine in water, that lone pair on the nitrogen sees the water molecules, and it does something very specific.
It grabs a hydrogen ion?
It grabs a proton, an H+, from a water molecule. It acts as a base. Now, when you take an H+ away from HO, what's left behind?
OH minus. Hydroxide ions.
Correct. And hydroxide ions are basic. They are what cause the color change. So the structure, that lone pair, is directly responsible for the bleed color you see.
That's a great connection. It's not magic, it's the lone pair doing its job. What about a technology application?
Okay, let's talk about clean water. Anion exchange resins. They are used in water treatment plants.
I've heard the term, but how do they work?
These resins contain tertiary amines, so our pyramid structure, but with 3 carbon groups attached. These amines are embedded in a polymer framework.
So millions of these little pyramids are stuck inside the filter.
Exactly. And when polluted water flows past, that lone pair on the nitrogen acts like a magnet. It attracts and captures negatively charged pollutants, anions, from the water.
So real-life clean water actually depends on that pyramidal structure and its lone pair.
It depends entirely on that lone pair being there to do the job.
That's amazing. From litmus paper to water filters, it's the same principle.
Yeah.
Now, you mentioned a catch earlier, a trap that students fall into.
Yes. This is where you have to be careful. You might think, okay, if all amines have this lone pair, they must all act the same.
Right. That sounds logical. A lone pair is a lone pair.
But actually, we have to look at the difference between aliphatic and aromatic amines.
Aromatic, like aniline, with the benzene ring.
Exactly like aniline. Now, in aniline, that red lone pair cloud doesn't just sit there. It gets pulled down into the benzene ring.
Pulled down? By what?
By the ring itself. The ring has a system of electrons, and it pulls the lone pair into it through resonance. The electrons get delocalized, they get spread out.
So the red cloud isn't as available anymore. It's distracted.
It's distracted. That's a perfect word for it. It's less available to grab protons because it's busy with the benzene ring.
Yeah.
So aromatic amines are generally weaker bases than aliphatic amines, where the lone pair is just sitting there fully ready to go.
That's a huge distinction. So the structure around the nitrogen controls how reactive it is.
Precisely. And that is a favorite question for the board examiners. Why is aniline a weaker base?
Okay, we're getting close to the end. I want to run through the clarity checks, the absolute must-know points for the exam.
Let's do it. These are the key takeaways for your revision.
Go for it.
Point number 1, availability. All amines have a nitrogen with a lone pair. This is the source of all their basic and nucleophilic character.
Got it. Lone pair equals source of power.
Point number 2, geometry. The nitrogen is sput or hybridized. The geometry is pyramidal, not planar.
Do not write planar. It is a pyramid.
Correct. Do not confuse this with the amatics. Point number 3, space. The lone pair occupies more space than a bonding pair.
Wait, why does it take up more space?
Because a bonding pair is held tightly between 2 atoms. A lone pair is only held by one, the nitrogen, so it spreads out more.
Fatter.
It's fatter. Okay, I'll remember that.
And the consequence is that it pushes the bonding pairs closer together. It compresses the bond angles, making them smaller than the standard 109.5 degrees.
That is a classic exam question right there, lone pair repulsion.
Exactly. Point number 4, bonding. Primary amines have 2 NH bonds, secondary have 1, tertiary have none. This is important for things like hydrogen bonding.
Which affects boiling points and all that.
Yes. And finally, point number 5, the aromatic distinction. In aniline, the lone pair delocalizes into the ring. This makes aromatic amines less nucleophilic.
Less reactive. The ring is hogging the electrons.
You got it?
Those are golden points. Okay, let's wrap this up with a quick summary.
Let's do a quick recap.
The core idea. An anamine is an ammonia derivative with a pyramidal shape.
And a critical lone pair on the nitrogen. Right. And for our mental image, remember the socket wrench or the blue pyramid with the glowing red antenna on top? That antenna is the lone pair.
And that structure explains the real world, why litmus turns blue, and how water filters work.
And for the exam, remember, nitrogen is spa hybridized, and that fat lone pair compresses the bond angle.
If you remember those points, you are in a very strong position for this unit.
You've got the structure down. Now you understand the soul of amine chemistry. And once you get that, the reactions will make so much more sense.
Absolutely. Structure determines everything.
Thank you so much for breaking this down for us. It has been a great deep dive.
My pleasure. Keep visualizing those molecules.
We will see you in the next deep dive. Until then, happy studying.